In this lecture, I want to talk about the idea of differentials, which is really related to the idea of a tangent line approximation to a curve. And what I mean by a tangent line approximation is being able to approximate the function values. So here, in this case, our function is 1.1s plus 0.05s squared. That's the purple curve here. So this is f. And I've drawn in the tangent line when s equals 30. So actually there's a real life scenario that this models, and f is the braking distance for a car at s miles per hour. So at 30, we could say f of 30, right? At 30, we should put that in, so that would be 1.1 times 30 plus 0.05 times 30 squared. You should get 78. So what this is saying is at 30 miles an hour, the braking distance should be 78 feet. Once the vehicle applies the brake, then it will take 78 feet to come to a complete stop. So the idea here is that near this point of tangency, so I've drawn in the tangent line at f of 30. Near in this area here, the values on the tangent line and the values on the function are very similar. We can just tell that graphically. There are situations that we run into where we have information about the rate of change of one quantity with respect to another, but we don't have any information, direct information about the original quantity. In other words, we might know something about the derivative, but we don't really know, we don't have a formula for the function. And in those cases, a tangent line approximation near the point in question could give us, we could use that to estimate what the function value is in that area. So let me just go through this example and then we'll get to the idea of differentials. So to find the slope of this tangent line, I would take the derivative, right, and evaluate it at 30. All right, so f prime of s first, that would give me 1.1, so 1.1s, take the derivative, becomes 1.1. Here I get 2 times 0.05, which gives me 0.1s. All right, so the slope of this tangent line, if I do f prime of 30, that's just going to be 1.1 plus 0.1 times 30. 0.1 times 30 should give me 3 plus 1.1 will give me 4.1. So that's the slope of this line. If I want to find the equation of the line, what I need is the point of tangency. Well, we actually already have the point of tangency, right? We know that that point, so this isn't really drawn to scale, that point there so this is f, this is s, that's 78 feet per 30 miles an hour, so this is the point 30, 78. All right, so to get the equation of my tangent line, I'm going to have y minus 78 equals 4.1 times s minus 30, which after I simplify, I get y equals 4.1s. So that's distributing and then bring the 78 over. I get 4.1s minus 45. So I can find the value of any point on the line using this equation here. All right, so let's use this to compare what our tangent line approximation would be to the actual function value. Again, graphically, it makes sense that if we're near the point of tangency, I mean, they're going to be the same at the point of tangency, right? If I put in 30 here, I would get back exactly 78. The value on the line and the value of the function are the same at that point because that is the point of tangency. But let's say we go out to 31, all right? Now if I put in 31 here, my tangent line approximation, 4.1 times 31 minus 45 would give me 82.1 feet. All right. So my tangent line approximation tells me that at 31 miles an hour, it'll take 82.1 feet to stop. If I use the actual function, f of 31, that gives me 82.15 feet. So you can see a very good approximation near the point of tangency. But what if we get farther away? What if we go out to, say, 40 miles an hour? Then our tangent line approximation would be 4.1 times 40 minus 45. And that would give me 119 feet of braking distance if I apply the brakes at 40 miles an hour. According to the function, though, if I plug that in here, then that actually gives me 124 feet. So we can see that where here the difference was only 0.05, 5/100ths of a foot. Here we see a difference of 5 feet at 40 miles an hour. And if we were to go smaller, the farther we get away from 30, it makes sense. You see this gap here gets bigger. Here in this area that I've circled, it's very close. The tangent line values and the function values are very similar. All right, so what's that have to do with differentials? So I want to begin by looking at this idea of differentials graphically. So I have kind of a similar looking curve here, and let's say we have this point C. This is the graph of f. So if I come up here and then come over to the y-axis, then say about right here, that's f of c. And let's say I move off of c just a little bit. We'll call it delta x. All right. So then out here I have c. My x value is c plus delta x. And again, I can come up to my function. So this is kind of blown up here, so we can kind of see this a little bit better. But here is f of c plus delta x. Because generally delta x represents a small change in x. This doesn't necessarily look so small, but I'm blowing it up so we can kind of see what's going on here. Okay, then right at this point, using another color, green was good, we can just draw in our tangent line. Okay, so notice first, before I talk more about the tangent line, that for this increase, this small increase in x, that the y value increases, right? F goes from f of c up to f of c plus delta x, and we call this difference delta y, right? It's the change in y, it's the change in the function value due to a small change in x. So what I'd like to look at on my tangent line then is how does this right here, so we can kind of look at this, right? Lines, constant rate of change, so I can kind of draw on this triangle. Here's my delta x, and this is what I'm using to approximate delta y. All right, so let's think about what that would be in terms of, we know that the slope of this line is f prime of c, right? So the slope is f prime of c, right? Because it's the derivative of the function at c, that's the slope of the tangent line. And slope is rise over run, because I want to figure out an expression for this rise here. All right, so if I take rise over run, and let's say I multiply both sides by run, so I would get f prime of c times whatever our run is along the x-axis. That would be our rise. But we already know what our run is, it's delta x. So this rise here, so f prime of c, since the run is delta x, this increase in the y value right along here is f prime of c times delta x. It's just the slope of the tangent line. So what we're doing, we're saying we take that slope and we play it out over another horizontal amount on the x-axis. If we move over, then this is the y value. So it's just the slope times that gives us the y value, or the change in y along the tangent line. Okay, so this is the idea. This is close to delta y, right? We see that there's a little bit of a difference here, and it gets bigger the farther we get away, but we are going to approximate delta y. So I'm going to say it's approximately f prime of c delta x. So we're going to call that expression dy. And this is the differential. All right, this is the differential with respect to y. In general, the differential with respect to x, we're just going to let that equal delta x. All right. So this is the relationship. This is where the differential comes in. It's our tangent line. It's the change in y that is that we get from the approximation using the tangent line versus the actual change in y. If we look at these two, the function evaluated at these two x values. So if we come back to our example here, all right. So the actual. So let's look at this first one right here. All right. So this tells me that the differential with respect to y, well, that's going to be. So we went from. We're using the approximation associated with 30, and we went up to 31. So we actually had an increase, right, from 78 to 82.1. Well, we know what that would be, right? It's going to be our slope. So the dy was 4.1, where this tells me that delta y is, 4.15. So where did this come from? Well, this is my 82.1 minus 78, and this comes from the 82.15 minus the 78. We're using 78 because that was my f of 30. All right. So the change in we changed in this case, looking at 31, our dx was 1. We increased x by 1, and the differential with respect to y was 4.1. Our y value, our approximated increase in y was 4.1, where the actual increase in y was 4.15. Down here, dy was bigger, right? So dy, we went from 78 up to 119, so dy was 41, where delta y was 46. So we see that the differential is very close to the actual change in the function when we're near the function at 31, and not as good when we get farther away. Okay, now let's just look at a couple of examples of how we might use differentials to solve problems. All right, so let's say I have a function y equals x cubed. All right, and I want to find both delta y and dy when x equals 1 and when delta x, which is the same thing as our differential with respect to x, equals 0.1. All right, so first, delta y, that's just going to be 1 plus 0.1 cubed minus 1 cubed. All right. More generally, if I wasn't working with this function, it's f of x plus delta x minus f of x. All right. So my x value is 1. My delta x is 0.1. All right. Minus f of x. All right. So this is going to give me. Let's see. It's going to be 1.331. If you take 1.1 and cube it, you get 1.331. If you take, that should be a cubed. If you take 1 and cube it, you get 1. So the change in y, the change in my function value, if I go from 1 to 0.1, is 0.331. That's delta y. Now dy is f prime of 1 times dx, or delta x, which are the same. So first, what I need is f prime. I need to find f prime of 1. So f prime of x is 3x squared. So f prime of 1 is 3 times 1 squared, which is just 3. So this part is 3. We already said that dx is 0.1. So that gives me 0.3. So dy is 0.3. Delta y, a little bit bigger. but we see that by staying close to, by having a small dx here, we can see that our tangent line approximation of the increase in y is very similar to the actual increase in y. Okay, last thing, I just want to give an example of some notation. This is called Leibniz notation. So if I let y equal x squared, then I'm looking at the change in y, dy, with respect to x, dy dx, and it's basically the change in y with respect to x, that's the derivative. So the derivative of x squared is 2x. And then one way of thinking about this is that I can multiply through by the dx, and I get dy equals 2x dx. So this gives me a formula for the differential. So up here I was working with a differential at a specific point, right? I'm at 1, I'm increasing by 0.1. My differential, my tangent line increase along the tangent line in the y value was 0.3. But this gives me a formula for any point along x squared. The change in y will be 2 times the x value times whatever the change in x is. All right? So here you can think of this as the slope. This is the slope of the tangent line, right? Because that's what the derivative is. This tells you the slope of the tangent line. This tells you the change in y on the tangent line, all right? And that can be used to approximate the change in the actual function value. Okay, so another example, just so we have one more, something like sine of 3x. So using the chain rule, we know that dy dx is 3 times the sine, derivative of sine is cosine, right? Okay, so it's 3 times cosine of 3x. So again, this is a formula for the slope. For any value of x, I can find the slope of the tangent line to this function by putting that value of x in here. If I want to find the change in y, the tangent line change in y, it's 3 times cosine of 3x, that gives me the slope, times whatever my change in x is. All right? So again, this just gives us a formula for the differential with respect to y. So it's not really a new idea. It's just, in some ways, it's almost just kind of a rearranging of the notation to give us a formula for the change in y along the tangent line. We can also actually compare the actual change in the function value with the tangent line approximation in the y values.